Welcome to the 1979 Nobel Prize in Physics. This one goes to Sheldon Glashow, Aldus Salam, and Steve Weinberg. Now, these three guys were theoretical physicists, and I mean that in the truest sense of the word. They worked at the fundamental levels of theory. Their work that they won the prize for was the unification of the weak and the electromagnetic forces. So officially, it was for the unification of weak and electromagnetic interactions between elementary particles, but really what they're talking about is the interaction of those forces. So what they managed to do was to say, look, these two forces are not really separate things; they're one thing, and there's some underlying mechanism kind of decaying, kind of controlling both of them. And what that does is say, hey, look, you really were interpreting it as two things, and really it's one thing. And why is that important? You know, who cares, right? Do you get this electromagnetic force? You got a weak force. Why not treat them separately? Why care if they're one thing? Well, it simplifies the math, first off. But again, it's, physicists, who cares? We're all good at math, right? We're supposed to be. Well, it does a little bit more than that. So let's take a little bit deeper dive and understand why the unification of these things really does truly matter. So when you're working down at the particle or nuclear level, what you want to do is be able to predict what's going to happen before you start messing around, right? Because E equals mc squared, and if you kind of let some m go and you create too much E, you've got a big problem, right? So you don't really want to have to say, hey, look, we don't completely understand it. We're just kind of guessing. We want to make sure we've got the math exactly right so that we can predict the outcome of a reaction before you take place, because that's kind of important. Particle physics, not as much, but nuclear physics, you kind of want to know this stuff, right? And those two worlds are kind of close to each other. So, but the importance of it really is to say, look, for a long time, we really were convinced that these two things were separate. These guys came along and said, hey, look, it's really one thing. And that really gave rise to a lot more renewed interest and a lot more focus on a grand unified theory. There was interest in it before that, but these guys started to break ground and say, hey, look, really, we can unify some of these things. And these guys really did it. And there are probably three guys you never heard of, right? Because, Einstein and others take all the press, but these three guys really did kind of do that first bit where you gave this unification to it. Um, and it gave a much more comprehensive view of particle physics, and it allowed people to understand how particle physics really works a little bit differently than what it does. And they predicted a couple of bosons, the W and Z boson in particular, that nobody thought would be there before then. Sure enough, they predicted them, and then they were proven later on. It also provided a framework for the Higgs mechanism, which really explains how particles acquire their mass. So we're really starting to understand how particles are built, how particles are formed, and really starting to understand that tiny little microscopic world of things, smaller than a proton and a neutron, how this little subatomic world really works because of things like this. Because without that unification of those forces, we don't have Higgs, we don't have certain bosons, and we don't have a deeper understanding of what goes on at this nuclear space. And it did give rise to a lot of renewed interest, like I said, in a grand unified theory. And although it has nothing to do with this particular Nobel Prize, let's talk about that for just a minute because it does get a lot of press. So, why is a grand unified theory important? So, a grand unified theory, what that would do in practice would take all the fundamental forces of nature and put them into one framework. It would simplify things so you don't have to try to figure out which one most applies the most. It would really simplify our understanding of nature's fundamental interactions and how nature really works. What can that do for us? Well, when we finally understood things like the photoelectric effect, it gave us everything from lasers to grocery store scanners. To solar cells, to whatever, right? When we finally started to understand some of the nuclear things, it gave us nuclear power plants. When we started to understand other bits and pieces of science, that something else fell out of it. So can I point to and say, this is what you'll get with a grand unified theory? Well, no, and neither can anybody else. But it is out there. It is one of those things we really want to get to because the more we understand it, the better off we're gonna be as a fundament as a science. And it would give us a ton of insights, we believe, into the early universe and how things really kind of formed and what was the Big Bang, how did that take place, and how did all this stuff kind of go out there. And maybe we'd sort out whether or not dark matter is real, and find the graviton. And perhaps with a grand unified theory, we can figure out if light really is the universal speed limit. Can we get faster? Are there ways to do interstellar travel? Who knows? We don't. There might be. But the limits of what we understand, it's not possible. Now, more importantly, if we had a unified theory, it would really give us help with testable predictions that some theories really have challenges with. And I'm looking at you, string theorists, because 11 dimensions, I mean, seriously, come on. It it really would help us with all those sort of testable things that we don't currently have on some of the latest and greatest theories, and I think that grand unified theory is out there. I think somebody's probably going to crack it, but who knows what it's going to look like in the end. And when that person does, they'll probably be met with some skepticism and say, oh, that can't be right. And then 5 or 6 years later, everybody will go, oh, well, they really were. That's the way these things work, because somebody's going to have to put their foot down and go, nope, this is how it is, and put their name and reputation on the line. I hope it happens in my lifetime. I would love to see it. But this particular Nobel Prize, like I said, doesn't really have a practical application, at least not yet. Maybe it will someday. It does give us more insight into particle physics, and really has ignited more into that grand unified theory. But to a physicist, this is sort of like, really cool stuff. So these guys did kind of rally the world into going towards that unification stuff, and did help us a lot with particle physics. So very important to scientists. Practical application, I couldn't think of one. If you know one, please drop me a line. But we'll see you on the 1980 Nobel Prize, which is coming up soon. So don't forget to click like and subscribe and the bell icon for notifications. We'll see you soon.